So now we are going to, so in the part 3, so part 3 was about health systems, and there was a basic part and a more advanced part. So we did the basic part just to learn the basics of the language, and hopefully maybe in the end of the afternoon or tomorrow we will see some more advanced concepts. Now I would like to leave this part 3 for a while and then go to part 4, where we are going to see how this applies to model plant development. So more precisely about plant processes. So just as an introduction, you can see the problem of modeling plants. There is no one way for modeling plants. There may be several, and I just give you two categories. The first, that I call descriptive, is the fact that you can look at a plant, look at even its development in time, and then, without knowing anything about how the plant functions, try to describe, like a painter, like an artist, to describe the way the plant is growing. Okay? So you don't need to grasp the essence of the processes that are behind. The other, so this would be the purely descriptive approach. And on the other end of what you have is the more mechanistic modeling. So I took an example coming from Michael Renton some years ago. And he made a development by computing the transport of carbon within the plant and then allocating the carbon to the different leaves. The leaves are intercepting light. And you see that you can recover all, well, not all, but a certain number of elements that are involved in the process of the plant growth. Okay, so it's more mechanistic approach here. So you have these two endpoints, mechanistic on the one hand, descriptive on the other. And of course, you could combine the two things. Let me just give you a few elements about the pros and the cons of these two approaches. And because they are a bit, at some point, it's difficult to join these two points together for a very good reason. Descriptive approach, you will be very faithful to the data. It's like you are a painter and you want to grasp every detail of the plant. So it's very good, and you can grasp the variability contained in the data doing this. So if you see different ways the branches occur in nature, you can make the distribution of these branches and then reproduce this distribution. But, so these are the very good points about this technique. The bad point is that it is extremely difficult to generalize to unobserved phenomena. Okay, so you grasp what you see, you make it very precise, the description or the model of what you see. But if you want to get out of it, to extrapolate, for instance, time that you didn't observe, or type of growth that you didn't observe, the model is not built in this way. On the other hand, the mechanistic approaches, they are quite to the contrary. What they are good is to explain the observed data and to generalize. Because if I make a model of a plant up to time t, then it's for me very easy to compute the plant up to time t plus 1, even if t plus 1 was not computed, because I have this type of laws inside my model that corresponds to the hypothesis behind. Okay? So it may be not true, but it gives at least some element on the prediction of the plant at time t plus delta t. But here, the descriptive approach was very good at reproducing the details, was very good at reproducing the variability. Here, the mechanistic approach are very bad at it. Because when I have a mechanism, it's very difficult to imagine how I should put noise in this mechanism so that, as a whole, after integration over time, all the accumulated noise provides the output that is integrated, that I see in nature with the variability that I see in nature. Okay? So basically here, I take conscious of the details and I describe the law at a local level. Here I don't look so much to the detailed laws, but I try to describe the overall encompassing laws of what I see. Okay, so I am actually at two different scales. Here I see from the outside. Here I see from the inside. Here I try to define local laws of the mechanisms behind the construction of my object. Here I describe the result. So at a more integrated level. So, but you can do combinations of these two phenomena to try to take the best of both approach. But at some point it will be difficult to combine it perfectly well together. Clear on this? And what I said is not only applicable to plants, but it's applicable to any type of modeling, actually, of nature. Okay, so we are going to review a number of ways to map the concept that we have seen yesterday in LPI form. For instance, we can start with the notion of monopodial growth. So remember, apical meristems, they grow indefinitely. The meristem, the axillary meristem, they get a bit older. They get older more quickly than the apical meristem, and they may undergo a differentiation into flower at some point. So, if you want to express this in a computer language like LPI, you would write typically something like this. So you don't need to write exactly these lines. It's just as a sort of schema of what you would have to write. You would say, okay, I have an apex, and this apex has an age. If it's an old apex, mature apex, like with an age, maximal age capital T, then it will produce a flower. If otherwise, so if the apex is younger than this, it will produce a lateral production and a new apex, that doesn't get older. So we could increment this one more fast than this one. Here I didn't increment the apex on the main axis, the age of the apex on the main axis. But here, what is important is that the age of the lateral is older than the age of the leader.
Well, you could not increase the age of the leader because you say it grows indefinitely.
Yes, I could, but I could say that this T is super big. Okay? I could increment this age, sure. And then in this case, I would need to go faster. It's just a relative, but you're right. Basically, you're right. So it's just to caricature a bit the stuff. Okay? So you can now try this example. It's example number 1 in this new. Okay, I updated the directory yesterday, and then you should be able to access the other practicals in the. So this would be in directory 4.1, something like this. You should be in directory 4.1 and example 1 in this directory. And here, okay, so you can play a bit with this model and play with the time capital T. Well, capital T is cycle number. And also, you see that the main meristem produces lateral meristem with a jump in the age that you can vary as well, and you can have and you can also vary the derivation length. So if I put, so this was 7. If I put 8, I could put the cycle number. So you can play with the parameter of the system a bit more, like 13 or 12. Cycle number, so the age is. So you see that the architecture of the plant will increase, depend, the size, the type, the number of flowers will depend on the relative position of these different parameters. You could also, so this is a 2D model. You could make it a 3D model just by putting a slash 137 degree, for instance, 137. And, well, maybe it won't work because the phyllotaxis. It's funny. It's not exactly what I wanted to obtain. It's because I have a plus and a minus. So I need to remove the plus and the minus here. Okay, so this is a plant in 3 dimensions. I just changed the phyllotaxis. So the same plant in 3 dimensions. Here I just modified this bit here, where I put the fact that the turtle should turn around the main apex, among the main axis by 137 degrees. And each time it produces a branch, it inclines with an angle of 45 degrees. Just to start to show you a bit like the 3D features will be used in the system. And you can augment the cycle number. And if you augment the cycle number, which is the capital T, then you see that before you reach a flower, it takes more time. So it means that the axis, everywhere where there is red, it will take more time to get to the red. So we build more branches. So this is how it goes. You have more branches. And you can still continue and have more branches. So, and just by manipulating this, you see this notion of data amplification. Because I changed almost nothing in my system. I just changed the jump or the cycle number, the capital T. And then the system is able to apply the rule again and again and again in a recursive manner, and then produces a structure that gets more and more complex, whereas the model is still the same, actually. Okay?
Why do you change the size of the turtle at the axis?
Here.
Yeah.
Because if you because of the overall scale that I used. Let me see. Yes, because my basic internode is of size 1, and obviously I will accumulate internodes of size 1 a number of times. You can see with the with the wireframe here. You can see how many internodes I put. See, 1, 2, 3, 4, 5, 6, etc. No. And if you don't put this, it will create it's a bit bizarre. Yes, because yes, sorry, I was a bit confused. It is because of this. The F here in the internode is not 1. I was looking at this, but it's not. The internode has a size. It is cycle number minus n. Cycle number is 15. So 15 is big. Okay. Minus n is minus the age. In the main trend, n is 0 because it doesn't change. Yes, it changes with time. So it's 0, then 1, then 2, then 3, then 4. So cycle number minus n, we get internodes reduce with the age of the production, with the age of the main apex. Okay. So but the initial size is 15. So I go from 15 to 0, meaning that this plant is super high. So if I want to adapt the diameter to 15, initially by default it is 0.1 the diameter. Yeah. So if I want to change the default, I need to put 1, and then it will be 15 against 1, 15 of length against 1 in diameter. Okay? So and this is always the case. Depending on the units that you use in your model, you need to adapt the allometry, what we call the allometry, which is the ratios between the different typical dimensions of your objects. So you need always to track this type of thing. Okay? Other questions?
Hey, could you re-explain the produce plus and produce minus for the expression order?
Yes, sorry. So I go back to the original code. I think this is it. Yes. Here, this one.
Yeah.
Yes. So plus and minus is for the turtle to turn left or right. And I want to have each internode, I want to alternate between left and right. So what I do here, I look at the parity at the evenness of the number. Yeah. If this is an even number, then I produce a plus. If this is an odd number, I produce a minus. And as the age, so you see A of n produces P of n. So the n is the age at which the internode was produced, or the lateral bud was produced, which means that depending on the rank at which the internode appears, it will be on the left or on the right.
But if you change it for a spiral phyllotaxis, then it doesn't make sense anymore.
Yes, yeah. Yes. This is why I had to change both things. You're right. Yes? No? All good? So now we can go to the other example with sympodial plant. So this was how to, in principle, to model a monopodial plant. And this is in principle how you would model a sympodial growth with two lateral buds. And again, we say that if I reach a certain age, I become a flower. And if if I am an apex, I produce lateral meristems, but immediately I jump to the final state, which will make it next time the flower. So which means that I grow an internode, and the apical meristem of this internode will differentiate immediately the next step into a flower. So it cannot grow anymore. So what will continue to grow are the lateral apices. Okay? So if you, yes?
Because your new meristems, they start from H plus 1.
Yeah, so they will differentiate a bit.
So everything goes faster.
Yes, they will actually they will count the time, because the apical meristem is age at a certain age, and produces lateral meristem at the next age. So with the time, this edge will become greater and greater and greater, and this will can be used by the plant to, for instance, to detect a moment where even the lateral buds, they should transform into a flower. And actually, you can test this with the program. Okay, so you see here that the plant produces an internode, then the internode the main apex differentiates into a flower, but the lateral buds, they can continue, but in turn they will differentiate, and their lateral buds will continue, etc. But in the end, if you grow sufficiently far, so derivation length equal, so you see that the maximal edge is 10. So here derivation length is 6, but if I go up to 10 or 11, then all the buds will finally get to a flower. And this is what we can test here. But the plant is actually already very big here. Okay? Answers your question? Okay. Other questions?
Yeah.
Yep.
If we come back just to the monopodial growth, the example just before.
Yep.
So at some point you define a...
Easy.
Yeah.
Yep.
Yeah. So in this example, you create a new entity, which is a P.
Yep.
And
P stands for phyllotaxis here. So it's just what would have been better is to include the P within the
I, no?
within the I or within the A.
Okay.
It's and well, this illustrates the fact that nothing is really done for once for all. You can imagine your way of programming these things.
Yeah.
There are many solutions actually for the same problem.
But you have to think before of the link between what you have in mind.
Yes,
in
exactly.
terms of- and the interpretation.
Exactly.
The interpretation.
And the closer it is to what is conceptually clear, the better it is for the implementation. Because in your mind, you have already made the work to separate clearly the things. Okay? Other questions? No? Then we can jump to the next slide. So this is a model that you can make with this type of... so if you go to 3D... Oh, not this one. I'm a bit messing up with the video projection and the slides, and it's a bit... So this is the type of plant. So it's not very polished, but this was done by high school students when they worked the flowers and the leaves and how the overall stuff should appear. And it is oleander. It's French for the French is the laurier rose. And you see that there in 3 dimensions you have this trichotomic plant where from each node there are 3 branches that leave, but the principle is still the same. You make a number of internodes, and then these flowers, and then you make a number of internodes, and then these flowers, and then only the laterals can grow out the whole plant structure. Okay, and what you note as well is that there are leaves in the last elements of the plant, but not in the beginning. Because the leaves, after some time, they are falling out of the plant. So you have this notion of pruning out the elements when they are too old. The plant gets rid of them. Okay? Now, if we spoke yesterday about architectural gradients. How do we implement this in this type of model? Here you could do this on a monopodial plant or sympodial plant, and in many different ways. So here I just created a small model that is example 3, where you can play with the possibility to change the geometric or the physiological property of the elements with a parameter corresponding to the architecture, to the spatial or topological place of the element in the plant. This can be the rank, this can be the order, this can be the height, this can be the altitude in the x coordinate, this can be the curvilinear abscissa along the stem. So you can imagine many things in order to control what is a gradient and what should vary with the gradient. And look, this is, I think, kind of interesting example, because you will see if you change parameters, the plant shape, the plant, what it looks like will drastically change. And you can reproduce, in a way, if you play around with the parameters, you can reproduce many familiar types of shapes that you see in nature. So just try to do it with your examples. So here, there is a new interesting thing. I don't know if you remarked. Yeah. So we have still the same principle, the same rule, the same production rule. Basically, an apex is producing an apex. Sorry, the line is folded. An apex produces an apex here with lateral apices, with lateral stuff here and here between the brackets. So there are two branches on both sides. And what I did, instead of putting directly something that represents the length, like 10, a number, a value, 10, I put a function in place of this value. And the function is defined above and says, given the argument, how should I compute the length? So it's a way not to directly give the length, but to interpret the length as a function of a certain parameter. Okay, so you have these functions defined here. And you see that I've put two types of functions, but you could try other ones. And then try other ones, and you will see that the gradients are extremely important in shaping the overall shape of the overall geometry of the plant. I do this with you. So this was inverse law. Now if I put a squared inverse, I don't remember whether it works. Okay, so you change completely the proportion of the plant, but you see that for instance here, I have, instead of putting a length that is decreasing with the altitude, with the height, in an inverse way, I said that it should decrease in the squared of inverse. And then you see that these translate into things that are shrinking much more rapidly than before. Okay? And you can see this type of architecture in some signs, in some inflorescences. And you see, if I put, instead of this, if I put a constant, like it could be 5, okay, then this changes completely the architecture of the plant. And you can do the same with the angle, with the phyllotaxis angle. And if you, again, I didn't change but I just changed I didn't change the length, but it's the same decreasing length as before. or it's not decreasing. No, it's constant. But you see that the change in the angle. So the angle is more open in the bases than at the top, and I could make it even more strong. Or it's no, sorry, it was augmenting. So it's augmenting towards the apex, and then you see that in the end it changes completely the shape of the plant, and then you can combine the two. For example, like this, and then again get a completely different perception of the plant. And obviously, so this type of analysis, amazingly, this was made by a Japanese guy. Just for the moment, his name is escaping me. He's very famous. Anyway, at the same time where the air systems were invented, so beginning of the 70s, let's say. And he was exploring why would plants get so many different architecture? Is it the fact that plants are playing on many variables, or is it the fact that they are playing a couple of variables, or say a few variables, but the impact on the plant is extremely is dramatic? And actually, what he find out, is our Honda. Sorry for the like the cars and yeah, and so if you find out that only by playing with a couple of parameters or a few geometric parameters, you can recapitulate a huge number of obviously well-known shape in nature, a bit caricatural like this one, but so it was really questioning how do plants control these parameters. So it was a bit anticipating the following years about the genetic analysis of the connection between genes and architecture on the other hand. Okay? Any question about the use of these functions? Is that okay, clear for everybody?
And just here in your model, why do you add another S segment in the prediction rule? So just before.
What was it?
So you've got
S of 0, 1
yes, S01. So
at the end of a
at the end, just before the apex, so you can.
Oh yes, it's so that you can see the apices, because otherwise all the small spheres. If I don't put anything, if I say I have let's say F internode, and they are so F, and laterally I have apices like A, and then I say that A should be a sphere of diameter of radius 1. Okay, so if I say this, what you will see is one sphere, because nothing moved. So in order to see the spheres, I just put before this f of 0.1, something like this, so that it creates, and a plus, you see, plus 30 degrees, so that I have a small segment here, and I see the two. It's like pedicel, if you like, if you want to have a botanical. Okay, other questions on this? But it's good, because we don't explain everything at once, but progressively we explain all different details. And actually, all these details you can find them in at any moment in any part of the code of any model.
And here, and here 0.1, so you don't need it in your code here. You could put S because you're never using any in the interpretation rule. You're not using this value.
Yes, it's here.
Ah yes, X, okay. Yeah.
S of X is F of X.
Yeah.
So this will be translated to F of 0.1, which is a bit a small segment.
It was before, in the example before, in the sympodial growth.
Okay.
Here you change it. So
Okay.
Could you remove the x of s?
Which one?
In the definition of s of x, could you change s?
Here?
Yes.
By what?
To change s of x by s.
No. Oh, well, you can do this, but it won't work because the system is looking for a module that has one argument.
No, but let's say you put s instead of s.
Ah, yes.
0, 1.
Yes. Because here, I don't. No, because there is 0.2 here, and this 0.2 would be interpreted as a constant if I do this, but it wouldn't change the shape of the plant. Okay. Good. I like that we go in this small because the point is that by understanding this, you start to really test your understanding of the overall system. So if you have no more question than this, I would say that you are on a good way to really understand how this works. Is it still difficult to understand are you building correctly in your mind the fact that the strings are rewritten and that everything is interpreted by the production rules? Does that start to be clear for you in mind? Yeah? Okay, good. Well done. Okay. Yes. What we can do is a funny stuff. Instead of controlling everything using function defined in the code, we could define functions with a graphical object. So I go to graphical parameter, I make a new panel. So the panel appears on the appears here, okay? And now in this panel, I right click and I create a new item, which is, let me see, which is a function here, okay? And then the function, I give it a name. I call it, I don't know, my func. Okay, and now I can edit. Okay, where is the problem? I can edit this function by using these control points here. Okay. And know that, so now this function is known to the system. So I can put it here. And I will link this function to my model. And how do I do this? Actually, through the name of the function itself. So instead of using length here, I will use my func. Okay? And it may be that I need to multiply by some scalar to scale the things, but we can try like this. Yes. Okay. So here, my func, there is, okay, the function here, now it works. I don't know why there was this problem. So the function here is defined between 0, you don't see well here, but probably if I manage to open this window a bit better. Okay, so this function is defined between 0 and 1. It's really a function. For each value in the abscissa, I get one value in the ordinates, y values. So it's a mathematical function. And this function returns a value between between 0 and 0.3. Maybe I can push it a bit. by making it an increasing function, or increasing and then decreasing, up to 0.5. So it means that what it will be returned by my function is a value between 0 and 0.5. Meaning that, and what I need to give as an input is a value between 0 and 1. As n, you see that I'm using n here. N is a value that goes from 1 to 6. I need to divide here by the maximum value of n, which is t. Okay, which is the maximum value that you can get in the count here to rescale, to normalize my value to 1. Okay, and now it should work, hopefully.
And does it produce a floating point, or because
it will produce a floating point, but here the s will be rewritten as an f, and the f can take a floating point. Okay, so if I run this, okay, so this is the raw result of my stuff. So what we see is that obviously what do you think occurred here? I have my idea. Why are all the elements big? It's again a matter of scaling in the system. Here, what is returned by my function here is something which is between 0 and 0.5. Okay, which means that the f that I'm going to draw is between 0 and 0.5. On the other hand, all my balls, the spheres that I'm drawing, they are 0.2 and 0.3. So they are. So the f will be of the same size as the radius. So if I want to have a bit bigger internodes, I need to multiply this by 10, let's say, 10 times. And then I will get the tree in this way. Okay? But no, look, this was all the purpose of this. Now, if I say that this function should control this function actually now controls the size of the internodes, and here the abscissa control the way the edge of the apex, so the edge of the apex, which is here, will be transformed into a length. Okay? And what it says is that as the edge is big, the length should be bigger. Okay? So now, if I want to control this through this function, I could click this auto update, and you will see that automatically the size of the tree will be changed. Like for instance, if I want to have small sign here instead of big one, I just decrease this value. Okay, no, I added a point.
You can have negative length.
No, or maybe, I don't remember, because this has changed. Okay, so this is a way, I'm adding points here. Here I have a plant where I have big entities in the beginning and small entities in the side, and you can see that this is the height of the plant. I have big entities in the beginning and small in the end. Okay? And you can do, and please do, same thing with angles. Did you manage to make this function? You can have very weird thing. Okay? Have you at least for some of you, managed to modify the angle in the same way? Could be nice that you try to do this so that you have a a feeling for how it works. And this possibility was introduced by the group of Przemek Brzezinkiewicz in the beginning of the year 2000. And this was a very efficient way to modify, for instance, the shape of a leaf, because if you have the venation, you can, or leaflets, you can modify the length of the leaflet or extremely easily. So it's a way to construct models in a very rapid manner, just by giving the profile of the different elements. The function that you are designing, you must remember that the argument should be normalized between 0 and 1, and then you need to normalize the variable that you want to pass on to this function between 0 and 1 before you call the function. Yes, actually, when you save your file, it will save the custom function at the same time. Actually, yes, it's a good point. All the things that you are doing in LPy, they will be saved exactly in the state where you, at the moment where you save, including the functions, including the different parameters and things like this. So at some point, if you want to save one state, you save, give a number corresponding to your state, and then you can save different states of your system. So before we skip to this next part, just to mention that gradients, usually in plants, they vary in time as well. Because what we were studying here is on a fixed plant, how to modify the gradients, but the plant was computed always at the same age. Now, it may be that in time, the function that represents the gradients in the plant varies as well. So the example number 3b gives you an illustration of this point, and then we can look at it here. I just kept as long as possible the example from the previous illustration. But I changed just the phyllotaxis here, and I added a parameter, which is the age of the phyllotaxis, which represents the time. And then I say the phyllotaxis will produce a left leaf or a left branch with a phyllotaxis multiplied by a certain scalar, 5, or with the phyllotaxis multiplied by a certain scalar, but in the other direction. So, which means that, what do you expect from this?
It will be close to the main axis at the tip of the...
At the tip, exactly. So it's a way to change well, actually it was shown here. It's a way to change the gradient as you change as you move in time. The angle, so you see this angle, maybe you should remark this. I will use something like this. This angle here is the same as this one. Is the same, well, these internodes, they are the same as this ones, they are the same as this one, they are the same as this one, they are the same as this one. And you see that the angle between the different elements is opening. Okay, you can even show it even more stronger. If instead of multiplying by 5, you multiply by 10, you will see the phenomenon even stronger. So meaning that when you animate the plant, what you will see is that I can do it for you. Okay, so this is it the plant? Yes. So if I animate the development of this plant, oops, sorry. What you see is the angle. I restart. I made it a bit strong here, the effect. The angle at the beginning is very sharp, and then for a given position, this angle will open with time. Okay, so this is a way, for instance. I think we don't remember whether we mentioned this yesterday, but the branch in a tree, usually they are in a tree or in many plants, huh? in inflorescences as well. It can be often the case. You have a main trunk like this, and the branch at the tip, they have a very sharp angle, but as you go, it can be even like this in the end, as you go towards the bottom of the plant, then this angle tends to open wider and wider and wider. But at the here at the beginning, it was a small thing like this. So this is at time t equal 10. At time t equal 1, this was a bit like this. So this angle, there was this one. This angle was not as open as it started to be. It was very sharp in the beginning, and then progressively this branch was opening in the course of time. Okay? So this is a very frequent phenomenon in plants. The fact that the insertion angle will change according to time, giving the overall shape of the plant throughout time. So remember this experiment from Isao Honda. The geometry, there are a few parameters: diameter, insertion angle, length, phyllotaxis. By playing with this, you can control extremely well the overall aspect of your plant. So sometimes, and sometimes it's really dramatic. So playing well with this is a key to model the development of a plant. And playing with the gradients. This is what we are investigating at that moment. Yes?
And so here, for example, if you would just say that, okay, this opening is just a consequence of the mechanical weight of the branch, which is wearing. So how would you implement this, like the effect of mechanics, for example? Would be a function depending on like the distribution of the weight?
It's good. It's a very good question because it makes it possible to illustrate what I was saying in the beginning. I was saying in the beginning, we are not looking at mechanics too much during this session because this would be yet another week of training. But so we are putting more focus on the geometric aspect of things. So you see here that in order to implement something that might be due to gravity, I don't use gravity at all. I just fake. I mean, I make it artificial, the fact that the plant will open, and I use actually a description. It's more a descriptive approach, because I say, I don't mind whether it's gravity or not. What I observe is that the angle is opening with time. So I just want to reproduce this. So this illustrates what we were saying this morning. But actually, you can do this. You can do the gravity effect, so you can do the opening of this angle due to gravity. But this would mean that you need to model gravity acting on these branches, understood as beams, like in physical mechanics, as beams that are bending due to gravity. It can be done, and actually there is an example. Normally it would have been in the course this afternoon. Actually, I can show it to you because maybe we cannot reach this example.
Basically, like in a formal way, you will introduce this. You will, in the code, the place where you will connect this gravity influence on the bending would be here, like instead of produce P and A+1, which is the simple way to fake the fact that the branch is bending. That would be here that you will integrate your
your You will express that you have torque that act on your system. That this force induces a displacement of your point, and you have laws to express this. And due to this displacement, you would have this opening of the angle. So I wouldn't even need to speak about the opening of the angle. This would be automatically taken into account by these laws.
And it will be case sensitive.
It's not case sensitive, but it would be context sensitive.
Sorry. Context sensitive.
Super good. Yeah.
Because it will be also affected by the
Exactly.
neighboring.
Exactly.
symbols.
Exactly. It's very clear. If I have, instead of using my hands, I can use a drawing. Very good remark. And this means that you are starting to be really in the right interpretation of what is going on. If I have a branch that is made of elements like this, I put it horizontal so that gravity can act well on it. Okay. If assuming that it's not exactly gravity, it's more like I have a fruit here that is creating a force at the tip of the branch. Then due to the torque, so here this is fixed in the trunk, and due to the torque that this is exerting on this element, the torque will propagate on the different element. So the torque propagates in this direction. So if you call T the torque induced by F propagates as a signal in this direction. And then the displacement propagates in this other direction, because the torque on this element, as this is fixed, will imply a displacement of this one. But then, due to this displacement, so the displacement should be now here, should lead to this new position of this endpoint. But now that I have this, I can compute the displacement of the next one, which is no longer in this way, which is more like this. And now I can compute the displacement of the next one, and now I can compute the displacement of the final one. And due to this, I'm able to recompute the overall shape of the plant, provided that the delta T between the two is relatively small. It's not too big, because I will need to have nonlinear laws otherwise. And in this case, you see that the displacement is computing in this direction. So to compute what occurs on an element, I need to know what is occurring here, which is this context sensitivity that you mentioned, in order to know what is happening here. But I also need to know what is happening here in a second step. So it's really context sensitive in one direction and then in the other direction. And this is exactly how it is implemented in the example. I don't know, number. We will see this afternoon. Yeah. Okay. Other questions? Okay. So let's try to work a bit with the phyllotaxis of plants. So we are not going in again. It's really an introductory course on plant growth. So we could have detailed models of phyllotaxis, and this is not what we are going to do now. What we would like is just from the outside, we're still thinking in terms of plant architecture. So we want to control the architecture of a stem. So basically, where are the leaves, what leaves there are, and this type of questions. So just a reminder, what we saw yesterday is that you have a number of types of phyllotaxis. You have spiral phyllotaxis, which is also called alternate. You have phyllotaxis with opposite leaf. We have more than one leaf on each node. The phyllotaxis can be opposite decussate, like this. You can have whorled phyllotaxis with several organs attached to the same node, more than two. You can have 4 and sometimes very many. And we want to draw stem that would have different types of phyllotaxis like this. What you need to know in terms of vocabulary, I remind you, I think we spoke of this yesterday. The angle between two consecutive organs on a plant is called the divergence angle. On elongated stem, it is very clear to see the angle. But on the sunflower, which is an inflorescence, actually, it's a lot of small flowers here. So you have a bunch of many flowers attached to the same receptacle. So here you cannot see the angle between two consecutive organs, and this is why it is making these beautiful spirals, by the way. So if you take one way. Do you know one way of computing this in the field? This angle, because it's not easy. You have plenty of leaves, so you could estimate this with the naked eye. This is one way, but there are more. Fabrice, can you tell them, or you remember?
So to measure it?
To measure it? No, well, no. I mean, okay, because Fabrice is really taking the brute force approach. He's taking a machine, put the plant inside, and then have a reference point, and then compute the actual azimuthal angle between two leaves, which is okay.
Counting the number of parasticks, like compact structures.
No, even not before this.
Yes,
We go in the field.
Yeah.
We look at a stem, and we want to estimate the angle alpha between two leaves.
So you get your blue. So you get the point where the two leaves are superimposing.
And
you count the number of them.
Exactly. I take one leaf. I look on the stem. Where is the leaf that is the closest on the top of this one? And this will make a number of leaves. I can count this number of leaves. 1, 2, 3, 4, 5, 6. And then what do I do?
You divide by
Divide what?
the term by the number of leaves.
2 pi? No, I need to count also the number of turns.
Yes.
And I divide the number of turns by the number of leaves. So for instance, here, I would go 1 turn, 2 turn, 3 turn, 4, 5. 5 turns. It's a bit difficult to see because in 3 dimensions, but it's very easy in the field. Okay? So I have 5 turns. 5 turns divided by how many leaves?
13.
So how many?
13.
13. Which is
138 degrees.
sorry?
138 degrees.
Okay, 38. Okay. It is because this fraction is an approximation of the golden number, actually. Okay. So it's very convenient in the field, and botanists actually they use to classify the plant phyllotaxis according to this fraction, which is actually, almost in most frequent case, close to a number close to 107 and 37 degrees. And now, look, if I'm compacting this structure, like a telescope, or how do you call this telescopic antenna. Okay, so this is what we just explained. If I'm compacting this, the two leaves that were above each other, they come to a proximity here. And this is why we are observing spirals in plants. Because this is not exactly commensurable with the number of turns, exact. So each time that you come back at the approximate position of the previous leaf, you shift a bit. But this shift will always be in the same direction because it is always the same approximation. And then it is the idea because you have why you have these spirals in plants. So this makes the connection between. But you see here that what is no longer accessible to me is this angle here. I cannot see it here. It's very difficult because it would be the angle between two consecutive leaves, and you see that these two leaves are not consecutive leaves on the stem. Yes? It's just basics about phyllotaxis. It's important to know because now when you go in the field and you see this, You can even show off with your children, you know. Okay. So question is how to build such a leafy stem in the computer, and you have this. Actually, it will be basically a rule like this one. You have this in the example 4, so you can upload example 4. So this is example 4 in 3 dimensions, and the question is how to transform this in a phyllotaxis with 137 degrees, how to augment how to change the insertion angle of the leaves, how to change the size of the leaf. So you can try to figure out rapidly a couple of these questions. In the description side here, you have hints on the questions that you could ask yourself.
And the L is a primitive from Pangaea?
Which, yes. Yeah, L is a primitive. It's like F, if you like. It's not L. It's tilde L. So here the module again. It's a bit of historical reason why it is this way. And it's a default simple primitive for plotting a leaf. Okay, so you could do many number of many things. Modify the orientation of the leaves, increase the diameter of the internodes to change the aspect ratios, shift the leaf blade. Yes, you see here that the leaf blade, so this is the main stem. There is a node here, and you have the leaf that has been plotted from the center, because the turtle is following a path that goes through the center of the stem. So the leaf is partly embedded within the stem. It's not very realistic. What we would prefer is to have a leaf that has even a petiole, but that starts at the periphery of the internode. So how to do this? So that to have more realistic representation of the plant. You can change the insertion angle. You can augment the number of leaves on the stem, the density. You can modify the size of the internodes. You can bend slightly the stem. So instead of having a leaf, after you draw the leaf, you could slightly bend the internode here, so that the overall impression is of a bent stem. So do you manage to make some of these questions? So let's try to do together something. We are going to make a series of steps. First step will be this one. Will be to change the nature of the leaf. If this comes on the screen, yes. So the leaf that you are using is a very simple leaf that is like a very simple polygon. We may change this by using more complex structures that are available in the LPI, actually in the plant GL library. And this is called a sweep surface. A sweep surface here. And for this, you need to give curves from which we will compute a surface. I will explain this a bit more in the afternoon. Just for now, because we just need to manipulate this, I need to define with the graphical panel that we already used, we need to define two curves and a function. The two curves, the yellow and the green, they will serve to represent the nerve of the petal or of the leaf. And the second curve will serve to represent the section. So like for instance, slightly curved like this. So you have, in the 4B, you have the leaf, okay? And you could play with the leaf parameter by changing the length and the width. Difference between curve and function. It's exactly the same difference as we have in mathematics. So a function goes from a certain interval, say 0 and 1, and associate with each value of x a single value at most in the y place, in the y space. So I would have something like this, but I cannot have this. Okay? Because this wouldn't be a function. So function is really this type of object. A curve, it's a bit different. It's a function, but not in the xy. So this would be xy. Is a function from 0, 1 to x1, to xy. To r like this, which makes it possible. So here, this. So let's say this would be a curve C, and a function would be a function of r or 0, 1. Okay, let's put it comes like this. No, sorry. The function will be from 0, 1 . Okay, so function would be from 0, 1. I had to map with the L pi function. Would be from 0, 1, which is x varying between 0 and 1, to r, where this is the y value. So if I want to have a point, I need to take a x, and then take the value x, and I get the value of y, and I have a point in the 2D space. If I want to have a point with a curve, I need to use a intermediate parameter, which is so often called t, or u, let's say u. And this parameter will vary between 0 and 1 and give me two elements, x of y and x of u and y of u. Like this. And then if I want to have a point, I change its value and I get two different values here. But now you see that with this, I can define, I can define things like this because I just have a parameter u that varies along the curve, but I have no constraint on the points, on the values that are taken in the r times r space. So I'm more free if I use this representation. So the function is this. Oh, sorry, a curve is this, and a function is this. So what you see of the function is not the u. What you see is the x of u, y of u on the function. Is that clear?
Yes.
And then it's very convenient because then you can vary a U. And then this is the basics for drawing surfaces in the 3 dimension. You use a U and a V. And we will see this a bit later.